Hey everybody, Professor Davis here from ChemSurvival.com and the YouTube channel ChemSurvival to talk to you a little bit about conformational analysis of butane using Newman projections. Now, butane is a pretty typical hydrocarbon for you to encounter during the early stages of your organic chemistry course, and it's ever so slightly more complex than ethane in the sense that it doesn't have just 6 hydrogen substituents around its central carbon atoms, but rather 4 hydrogens and 2 methyl groups, and that adds a whole new level of complexity to its conformational analysis. And we're going to take a look at that in just a moment. But first, let's get a quick refresher about how to do a conformational analysis using Newman projections and the simplest possible example of ethane. Okay, so the conformational energy diagram for ethane looks something like this, with an energy axis on the vertical and relative rotation plotted as my independent variable. And when I look at a molecule of ethane down the carbon-carbon bond like this, I can clearly see why we have local minima and maxima. The local minima in the energy correspond to the staggered conformation. And a 60-degree rotation leads me to the local maxima, which are the eclipsed conformations. And in the case of the ethane molecule, I can do this pretty quickly because all 3 of those staggered and eclipsed configurations, relatively speaking, have the same energy. But this is not going to be true of butane, so let's take a look at what happens when we add something besides just hydrogens to these 6 positions that stand out during our Newman projection. So now let's take a look at butane, which is a hydrocarbon with the molecular formula C4H10. Now, butane looks like this, and it has 4 carbons in a linear chain. So naturally there are 3 different carbon-carbon bonds along which I could cite for my conformational analysis. I'm choosing to do my conformational analysis along the central bond, or the C2-C3 axis. This is because it's going to give me the most interesting result when I do it. So if I cite along this axis, notice that each carbon will have 2 hydrogen and 1 methyl substituent. When I do my conformational analysis, what I see is a conformational energy diagram that looks something like this. Very similar to ethane in the sense that there are local minima and maxima, which correspond to staggered and eclipsed conformers. And yet somewhat different, because if you look closely you'll notice that not all of the staggered conformers have the same energy, nor do all of the eclipsed conformers have the same energy. So there's something more going on here in butane than there was in ethane. And in order to explain this better, I'm going to have to turn my molecule on its side and cite along the carbon-carbon bond in a Newman projection orientation. And when I do this, as I've drawn it, you can see very clearly that the 2 methyl groups are at a 180-degree dihedral angle to one another. So they're as far apart in space as they can possibly be. When we have a molecule like butane, in a conformation in which the largest substituents are as far as possible from one another, we refer to this as an anti-conformer. The anti-conformer is, of course, the lowest energy conformation possible, because there's as much space as possible between the largest groups. A 60-degree rotation of the carbon-carbon bond leads me to my first eclipsed conformation. And you'll notice that although this is higher in energy than the anti-conformation, it's not yet the highest energy conformer, because my methyl groups are each eclipsing a hydrogen. My next 60-degree bond rotation leads me to another staggered conformer. But in this staggered conformer, you'll notice that the methyl groups are getting very close to one another. So when we have a situation like this, where our bond conformation is staggered, but the largest groups are adjacent to one another, we call this a gauche conformation. And it's slightly higher in energy than an anti. Proceeding through another 60-degree rotation takes me to my least stable conformation, one in which the 2 methyl groups eclipse one another. When the 2 largest groups eclipse one another, we refer to this as a syn conformer. And the syn conformer is always the highest energy possibility. Another 60-degree rotation will take me back to another gauche orientation. Yet another 60-degree rotation leads me again to an eclipsed conformer in which my largest substituents are eclipsing smaller ones. And my final 60-degree rotation will bring me back to my starting point in an anti-conformation. So as you can see, it's all about the relative position of the larger groups in our Newman projection that tells us whether we're in anti, eclipsed, gauche, or syn conformations. And a molecule like butane is an excellent example of this. I hope this was helpful to everybody. I'm Professor Davis from ChemSurvival.com and the YouTube channel ChemSurvival. I'll see you next time. Clocks, mugs, calendars, t-shirts, I'm always adding something new at ChemistryGiftShop.com in the Cafe Press Marketplace. Stop by and see us sometime.